Okay. Hi, everyone. Welcome back. It's 1 minute till we start, but just a couple ground rules before we get going. First of all, my name is Ori Fox. I'll be chairing this session, which is a little bit more focused, type 1As, whatever, but this is the, meat of the conference, the core collapse supernovae. And a couple ground rules. I was reminded that in Slack, we want to really focus having you post your questions under the thread for each of the speakers, which is now designated. So do not post here in Zoom or in the general Slack thread. You'll see each speaker listed in session 3. Or actually, what are we session? Yeah, session 3. All right, so let's get going to make sure that Sebastiano has all the time dedicated to him. This is Sebastiano Calchi-Novati from Caltech, who will be speaking about microlensing with the Roman Galactic Exoplanet Survey.
Okay, thanks. So I am going to move in the framework established by a partner network for the Roman Galactic Bulge Time Domain Survey. I'm going to focus on the detector simulation, which has been developed within the Microlensing Science Investigation team, led by Scott Cowdy, while it's now over. In particular, I would like to acknowledge collaboration from Sean Curry and Matthew Penny. And I'm going to put this in connection to the role played by the IPAC for this survey. So the Roman Galactic Bulge Time Domain Survey, in a nutshell, the notional survey observational strategy, 2 square degree, almost right at the galactic center, duration 60-72 days per 6 seasons along the 5 years of the mission, cadence 15 minutes in the primary wide filter, expected yield several 10,000 of microlensing events and about 1,000 bound exoplanets, with the bonus of free floating planets. So an example of a microlensing event is shown here with the planetary perturbation, and the kind of science that should be achieved, we want to achieve, is that the census of for the exoplanet population. All these plots and the yield are taken from the paper by Matthew Penny in 2019. So expected data volume is quite large, 40,000 epochs in the wide filter for of order of 10 to the 8 monitored stars, and of course we don't know a priori which one are going to be microlensed. So IPAC, or I should say the Science Support Center, SSC at IPAC, has several responsibilities within the Roman project. Well, I'm not going to enter this, just I'm going to refer that it hosts the Microlensing Science Operations System, or MSOS. So the high-level data flow, data from the Roman down to ground to Space Telescope, or the Science Operations Center, SOC, for the initial basic reduction. Then this level 2 data will be sent to IPAC for additional reduction, and particular for getting level 3 and 4 microlensing data products, which then are going to be sent back to the Space Telescope for archive, where they are going to be available to the science fiction team, whatever it's going to be called, and to the community at large for further analysis. So what kind of analysis is going to be done within MSOS? So starting from the images, we get 2 light curves. So first of all, you have to establish the catalog of monitored sources, and then getting the photometry and plus a few additional ancillary products. Then from light curves to microlensing events. So detect microlensing events, characterize them both in microlensing parameter space and in the physical parameter space, in particular for exoplanets. And this is to be due both for data and also for simulated data, so to establish detection efficiency, which is also part of the MSOS goal. So the detector simulation enters into this framework naturally, as it can be used as a test bed for the MSOS pipeline. So within the microcity, it was rather, the focus was rather on assessing the impact on the photometry and astrometry, and in particular, of course, for the planetary microlensing events of various effects. Well, first of all, of course, we have all the astrophysical effects, the underlying photon noise, crowding, Doppler motion. Well, of course, we do want stars to move to get microlensing events, but then it's a little bit of a nuisance in the analysis, PSF variation due to, for instance, variation with the spectral type. And then there are several detector observatory effects, which also should be taken into account, additional source of noise, readout, thermal noise, then jitter, and then various possible systematic effects coming from, I don't know, interpixel sensitivity variation, nonlinearities, battery factor effect, persistence, and so on. So Toolbox for the simulation, which I stress is just an image and star simulation, so only point-like objects are simulated. The astrophysical scene and the Microlensing population, all this is taken in input from GALS, so the work by Matthew Penny, from which we also take basic instrument and observatory models and noise specification, for which, however, we also take into account various sources related to the Roman project. So we also take advantage of external simulation tool made available in particular by Space Telescope. In particular, we use WebPSF for the model of the PSF. For the image simulation itself, we build upon previous work on Spitzer hierarchy data, but basically this follows the strategy as outlined by Anderson and King in 2000 with the EPSF formalism suitable for undersample detector. For the Microlensing magnification, we use the public available library VB binary lensing developed by Valerio Bozza. So this is an example of a 2x2 simulated image. So there's just 1/16 of one 4K by 4K detector, so a lot of star, and also note the structure of the PSF. So for the simulation in input, we start with the oversample PSF. Then the simulation is carried out either at subpixel or pixel level with this, say, EPSF way like. It can be generalized using several PSF to account for variation across the field of view or variation with the spectral type. We simulate the background, so detector plus sky and corresponding noise. Then we loop over the star catalog and simulate stars with the corresponding photon noise and wrap up with a model of the read noise. And optionally, we can include additional detector observatory effects beyond this, let's say, ideal noise realization. In output, we have the, say, the images and the corresponding uncertainty maps. And we can also get some, say, test photometry and astrometry. For the star, I stress this is test in that we are using the input catalog and the input PSF, so it's kind of cheating. So a few characteristics. Well, when we look at the photometry, we have several sources of noise. If we take just a simple case of one isolated star, where we have, first of all, the basic photon noise, it's in the black dot, then several sources of noise, readout, sky, dark, and thermal noise, all with their contribution, and note the near around magnitude 21, 22, where this background noise tend to be start being relevant versus the photon noise. However, one major source of noise for the galactic for the bulge survey will come from the scene. As of course, we can hopefully get to remove the signal of nearby star, but we cannot really remove their noise. So here in this plot, I'm showing the histogram for the noise associated from the star in the field, as compared also to noise from, say, readout noise in thermal and dark. The impact of crowding is also visible in this plot here on the right, where I show the luminosity function and the distance in pixels to the nearest star, say bright enough, that's the one we are looking at. So in black, it's the full sample, and in blue and red, what we get to recover when we carry out the analysis, taking into account or not the presence of nearby stars. Of course, it is essential to take this into account for a proper analysis. Note also that the typical distance to a nearby bright star is going to be around 1 point something pixel, which is just about the full width maximum for this for the W5 detector, which is rather undersampled. So we do simulate several effects here. I'm going to briefly describe a couple of these. So of course, it is key to get reliable models for these effects in order to get a meaningful simulation. For the jitter, kind of high frequency oscillation of the observatory, we model them by summing up for each exposure several sub-exposure, which each one is slightly offset versus the previous one. So the key parameters here are the frequency and the model for the offset. In the fiducial model, we combine two modes. And one to simulate the fine grinding system, and the second it's a higher frequency random walk, and overall this gives rise to a broadening of the PSF and a slightly offset versus the nominal position, which both impact the astrometry and photometry precision. Another potentially relevant effect is persistence. So this is known to be quite a big issue for previous generation detector like WFC3 for HST. However, so this kind of ghost image coming from earlier exposure. However, it has been shown that that for Roman WFI detector in particular, those qualified for flight, the impact should not be so bad. So here, the basic persistence simulation consists of getting a map of the persistence from previous images, as shown here. And then in the actual image, we get this
two minutes.
Okay, additional fake star as compared to the situation where we don't have this. So this may introduce additional noise. So we also simulate microlensing events, of course, that's the main point. As discussed by Aparna, a key point is that with Roman, is going to be the first time where the microlensing survey will, the same data set will also allow simultaneously high resolution imaging to get to the lens flux analysis, which is relevant to get to the physical parameter of the lens. So I'm showing here an example in pixel space of the lens and the source moving toward each other. So this is both proper motion and parallactic motion, and this is the resulting microlensing events, in this case with overlapped a planetary perturbation. So this detector simulation can be used, as I mentioned at the beginning, as a prototype, as a test bed for the pipeline developed at IPAC. Here I'm showing a few prototype analysis, in part based upon codes developed by Jay Anderson within the microSIT. So we start from a series of simulated images, which are the output of the detector simulation. One example is shown here. We get to the stacked reference frame is shown here. So it's a stack of here 750 images with times 8 oversampling, out of which we can get the EPSF and then extract the star catalog. The nice, and here is the residual, the reference minus the model for the star catalog. The nice point here is that the EPSF, which can be used one-to-one versus the stack versus the reference frame, can be used as, say, traditional EPSF on the original images to get the photometry. And as for the star catalog, here preliminary results show that we get to recover quite well all the underlying star distribution. And with that, I see the time is over, and so I close and take questions. Thanks.
Okay, thank you. Thank you for that very nice summary of the microlensing simulations.